Okay. So welcome to today's class. Today, Professor Seth is traveling for a conference, so I'm taking the duty of him. So I'm introducing Aman Chetta from Amazon. He's a nice friend and long-time collaborator. So Aman graduated from UW Medicine. I believe he is currently pursuing his graduate study in Stanford. He's in Amazon quite in a leadership role. I've been actively working on various aspects of generative AI. And we have been collaborating for how long I don't remember now. We published so many papers together. And good to have you, Aman. Over to you.
Thanks for the warm welcome, Dr. Das. Indeed, it's been so many years, even I can't recall a lot of great collaborations. But yeah, let's begin with the presentation for today. Dr. Das actually introduced me to Prezi, the presentation tool that I'll be using today. I think it's a fantastic tool. But let's dive right into Agentic AI, the topic for today. So what I'll be covering today is essentially the framework of Agentic AI, what it means to have an AI agent. Then I'll be covering some design patterns, benchmarks. How do you evaluate something that's an agent, right? How do you know if the agent is doing the right thing or not? And what are some leading benchmarks currently in the field? And lastly, we'll touch upon some papers that have been pretty instrumental in the field of agentic AI. So that's the agenda for today. And without further ado, let's dive right in. So let's start with the framework. And like I said, then we'll go over design patterns, benchmarks, and papers. So here's a rough definition of what it means to be an AI agent, right? AI agents are autonomous systems that combine decision-making and taking action, carrying out a particular task based on some language processing by an LLM. So that is the rough definition of an agent. And the reason why I choose the word rough here is agents are ever evolving. We have a lot of work being done in the field. So this definition is also changing over time. There's more capabilities and possibilities being added with agents. So we'll see this transitioning further, with more added capabilities to this definition over time. And if you look at the diagram on the right, you'll see that at the core is your agent, and there's a whole lot of other aspects around it. There's memory, there's tools, there's actions, there's the agent interacting with the environment, there's planning happening, and there's certain goals that we require the agent to perform. And then obviously there's the user, right? So the way this is structured is that the LLM is essentially the brain here. It's the orchestrator that is interpreting the query coming in from the user and figuring out what are the potential next steps to carry out this query, right? Do we require reasoning? Do we require some planning? Do we require tool use? Do we require memory, short-term memory and long-term memory, as we'll talk about in the coming slides? So all of these different aspects is what are orchestrated by the LLM, which is the central orchestrator or the brain of the entire system. So the workflow cycle here is essentially analyzing, planning, like I mentioned earlier, and then figuring out in real time based on feedback of what, the interaction that have happened previously, which are stored in memory, figuring out what is the best path forward in solving this particular problem statement that's been posed by the user. So I'm sure you guys have heard, a lot about agents here and there in research, and just like we had the ChatGPT moment back a couple of years ago, it was a pivotal moment in AI. All of us were pretty surprised with a lot of the possibilities that ChatGPT opened up. In a similar fashion, we've got the agentic AI moment happening right now, where we're seeing LLMs go way beyond what they were initially capable of, taking action via calling various APIs, tools, remembering prior preferences based on memory, both short-term and long-term. So there's a whole lot of these different aspects that are pretty central to, the agentic AI movement that has arrived, similar to what we saw with ChatGPT a couple of years ago. All right, now let's touch upon the agentic workflow at a top level. What does it mean to run something by an agent, right? So typical LLMs, if you take an LLM out of the box, it'll generate an output in one shot, right? So if you feed it a prompt, out comes the output sample token by token. But when we add an agentic aspect to this particular workflow, we are essentially saying that we want something iterative. We want something that is a multi-step refinement of what we saw previously with just using the LLM out of the box. And what this exactly means is that as part of once we feed in the input query, as part of processing that query, the agentic workflow here carries out initial task planning. It figures out a rough outline of what it means to execute this task. And then for each of these sub-steps, it figures out if additional information, knowledge, or research is needed, right? Does it need to pull in information from the web? Does it need to look up a knowledge base, such as a vector database? Does it need to look at other forms of knowledge that are available, right? It could be your calendar entries, email, if you're asking the agent to say schedule a meeting for you in an available slot. So all of this augmented information gets pulled in from relevant sources. And then once it has access to the outline, additional research that had to be done for each step, that is when it actually starts processing this particular prompt, this expanded prompt with all of this relevant detail to give you an output, right? So this is an iterative workflow, right? So you'll see that the LLM is called multiple times as it chalks out a plan, as it chalks out additional information that's needed, calls APIs to gather all of that information, and finally generates the output, right? Earlier, all of this was still possible, but we could only do it in a one-shot level, right? So it could come up with some rough plan and then essentially give you the output in the same iteration itself, right? So there wasn't as much of an iterative workflow that was involved. Now, the last part here is that if you look at how humans think, right? This has a very interesting parallel with how humans refine their thought process over time, gathering additional details, coming up with a rough idea, task plan of what it means to achieve a particular task, executing on it step by step, and with all of that relevant detail, finally getting to results, right? So this is, in a way, mimicking some of that human thought process, the iterative flow that agentic AI involves. All right, and feel free if there's questions, feel free to stop me, or maybe we can use the chat and then take questions at the end. I think that'd be great. But yeah, got a lot of topics to cover within the agentic AI, so I'm just going to go through it one by one. So what I have here is an example of an agentic workflow, and this is a poster child standard example right now in the field, software engineering. There's a whole lot of startups right now doubling down on this particular piece because the nature of software development lends itself naturally to what agentic AI has to offer. Because software has all of these various components. You're writing your primary code, you're writing unit tests around that code, there's integration tests or system tests further on. There's code guidelines with Python. We have PEP guidelines, for example, that need to be that you need to follow to write code that's high quality. So all of these are various agents, right? And if you can distribute a task into various different chunks, that lends itself naturally to an agentic workflow. So software engineering, like I said, is a classic example. On the right, you'll see that going from GPT 3.5 to GPT-4 on human eval, which is probably the most common code development benchmark out there. You'll see that with agentic workflows, the performance with GPT 3.5 tends to reach or even surpass performance on GPT-4 just by using an agentic workflow. So what this tells us is that agentic workflows are here to stay, and they do really have an impact in real world use cases, right? And on the bottom right, I've got Devin, which this is a startup Cognition that introduced Devin, which is the world's first AI software engineer. They had a very splashy demo a couple of months ago, I believe, and they actually showed on a very popular benchmark. It's called SWE-bench, a software engineering benchmark. They had some of the best results out there, and all thanks to an agentic workflow that they put together. So software engineering is about to, transform itself as a field thanks to agentic processing. And like I said, because of how the task is structured, and the way it lends itself naturally to some of this chunking into various different components, which are essentially agents at the end of the day that carry out unit test writing or system tests, or even coding up the primary pieces of your code and putting it all together as an integration engineer as well. So all of these components can be modeled as agents. All right. Now, lastly, let's get to the biggest chunk of this particular piece of today's presentation, the framework itself, right? So what we have here is essentially the core right at the center, which is the decision-making engine, which is like I mentioned earlier, that's the LLM, which is carrying out the high-level reasoning and orchestrating across all of these other components around it. We've got the memory module, and like I mentioned earlier, we've got two types of memory that we look at. It's short-term memory, and that can be modeled just through the prompt itself. You could introduce a retrieval augmented generation pipeline, which picks up, whatever is relevant about the particular user. So if you want to say personalize something based on prior user interactions, you could utilize a vector database at the back end and retrieve from that via RAG pipeline back into the LLM's prompt, and that will serve as short-term memory. Long-term memory could also be modeled with a vector database, but you could expand the time horizon for the entries that you look at as you're retrieving. So that's one form of modeling short-term and long-term memory. But there's various implementations now out there to carry out, to offer various different options for both short-term and long-term memory. Tools are probably the most important, part of this puzzle. Having the LLM understand what it means to call a particular tool and in which scenarios is a particular tool relevant, right? Given a list of, say, 10 tools or 10 APIs, which one does the LLM call based on the input query, right? So being able to pre-train the LLM on a lot of the data sets that are currently available for tool calling. Open Functions by Berkeley is a very popular one. You've got Hermes function calling is another one, and I'll touch upon some of the data sets as well. So once the LLM understand what it means to call a tool, I think that unlocks a whole lot of possibilities. And like I said, we've got a bunch of data sets for that. We've got frameworks like LangChain that help us orchestrate all of this and put all of these blocks together, glue them with glue logic for the model to understand what your APIs are and structure the prompt in, with some few short examples as well for calling APIs. So putting all of that together, hooking it up with a vector database at the back end for memory. So these frameworks are pretty instrumental to put all of these blocks together. We've got LangChain, Crew AI, Swarm by OpenAI, a whole lot of different Baby AGI, a whole lot of different options right now. And lastly, planning module. This is particularly important as well because as you go from a complex problem statement, one that involves multiple different pieces, how do you decompose that problem statement into steps, right? Into substeps that will help you achieve the end goal, the end problem statement that you're looking to solve, right? So that planning aspect or the decomposition aspect is pretty important as well. So these are the four different components of. Sorry, I think there was some background noise. Do we have a question or can we proceed?
No, you can proceed. I think there was just a mute.
No worries. No worries. Yeah, so these are the four important components of what it means to have an agent, right? Right from the core to the memory modules around it, the tool calling capability, and the planning aspect, the task decomposition aspect. All right, so that completes the framework part of today's presentation. Now we'll touch upon the reflection part, which is one of the most popular agentic AI design patterns. And the next four or so sections of this presentation are going to be typical design patterns that we see in the field when we say that we're using agents. These are some of the most common patterns that we've seen. So let's hold on. Let me see if yeah. So let's actually talk about function or tool calling first, right? So tool use in LLMs is essentially, like I just mentioned, is a very important capability, right? Out of the box, an LLM is confined to the knowledge that it has seen during pre-training, supervised fine-tuning, and some stylistic alignment as well later on if you have an alignment stage. But beyond that, the LLM does not have access to the web, or can't even carry out calculations, arithmetic calculations in some cases, let alone word problems and such. So having the LLM go beyond what it's trained on and have it get access to external information is what API calling or tool calling offers, right? And to give you a couple of very simple examples, if you make an LLM generate some code, right? If you take code LLM, if you take GPT out of the box and say, hey, write me code for this particular use case, the model is able to put code together, but for it to be able to run that code and understand if this code is runnable, does it have errors, syntax issues, or are there functional issues? Understanding a whole lot of that requires it to have access to the Python code interpreter, assuming you're using Python here. But I mean, the same idea is extendable to any kind of language here, right? So being able to, for it to be able to call a particular API, send over the code that it has generated, and thus validate that what it has at its output is something that is usable, requires access to the Python interpreter, right? And that becomes an agent in this case, right? So code interpreter is actually a standard agent that GPT-4 uses to essentially be able to run its code and certify that this code is runnable, it's free of issues. So that's a classic example of an agent. And same thing with SQL queries. We have SQL agents as well that are able to run, say, text to SQL, prompts. If you prompt the model with, the schema of your particular database and ask it to generate a particular query, it's able to use the SQL environment that you've set up and modeled as an API, call that API by generating token by token the API call, and run that particular query and figure out if this is runnable, extract the output, get the output back within its prompt, and actually tell you that it ran successfully. So this particular idea behind being able to run code through interpreters or even queries is a very classic example for function calling. And same goes for accessing real-time information, right? Web search is a very common, aspect of what makes LLMs good, right? If you ask about an LLM about, say, recent election results, it obviously, but just based on the data that it was trained on, and typically these LLMs are trained on data that's a couple of months in the past, right? Um, Based on that information, it can't tell you what the latest election results were, right, from a couple of days ago. So having access to all that real-time information, recent events around the world, or factual information, a lot of that does require web search. And that is, again, an example of a tool that the LLM can call if it needs to figure out, events and information beyond its knowledge cutoff, right? So that's another classic example. And in fact, what we do here is that we pre-train these models on data that tells it how to map a particular input query to a particular function call. And like I mentioned earlier, there's a whole lot of different pre-training data sets available, open functions from Berkeley, Hermes function calling from Noose Research, a lot of different options. Salesforce has XLAM as well. And once it knows how to do this mapping, going from the input query to a particular function call that serves this particular query, uh, at runtime, we're able to offer this model a whole lot of different examples for APIs that pertain to your specific environment, right? So say if you have a particular business use case, or you are doing research and require the model to call a certain set of APIs, right? In the prompt, you could have a whole lot of these APIs, and we typically model these as JSON objects. This is implementation detail, but you can model it in a whole lot of different ways. But the idea is to tell the model what the name of the function is, what are the various different arguments to this particular function, the type of data that each argument expects and model that as a JSON object within the prompt. And essentially, you can show examples also of going from an input query to this particular function being called there by doing few shot learning for each of the functions within the prompt, and then set this prompt up together and feed that to the LLM. And at runtime, as you put in a query, it should be able to go from that particular input to a particular function call based in your environment, whatever is available to you with the right set of arguments. So that is the entire idea behind the function selection mechanism, going from a relevant input query to the function call that maps to that particular query and is able to come up with a relevant output based on what the query is looking the LLM to do. Now, one thing is, say, if you have thousands of function calls, in fact, in research, we have papers now looking at millions of APIs. How do you feed all of this into the prompt of the LLM, right? That becomes a challenge unless you're using, one of the long context window LLMs like Gemini, for example, with a couple of million 2 million right now, I think, is the latest with Gemini, and 10 million is already being experimented in research as far as the context window goes. And even if you can feed it all into the prompt, that's not as efficient, right? So people have come up with retrieval augmented generation methods here as well, where based on the query, we look up a particular vector database and figure out what are the most relevant function calls that can be executed based on the nature of the query, retrieve that back into the LLM's prompt, and then at runtime, make a dynamic selection. It could be one particular call, it could be multiple calls, and I'll talk more about the different forms of API calling as well. We're not limited to a single function call, to serve a particular input query. We have various different patterns there. Also, the single, there's multiple, there's parallel and multiple parallel. There's 4 different strategies, and we'll touch upon that in a later slide. But depending on whatever pattern it is, it figures out what are the most relevant calls, function calls to be done, retrieves them, and then that is when the LLM has access to the various function calls that it needs to look through and figure out what is the best strategy to execute based on the input query that was posed by the user. So a lot of complexity beyond just a single function call that can be executed to serve a particular input query. And like I said, we'll touch upon that as well. And as an example, what I have here is web search and code execution. And we just touched upon that in the prior slide as well, right? So this follows along from that slide, where based on user input, if the LLM figures out that it needs to do a web search to gather some real-time data or to execute some code, if you've asked it to, say, carry out a mathematical task that it's not good at out of the box, or if you've asked it to just write code for a certain use case, it understands that it needs to, be able to use the code interpreter to verify some of its generated code. So that is the context-aware tool or API selection part of this particular piece. And as an example, if you look at the diagram on the right, you'll see that the LLM is trying to call the Bing Copilot when it's asked for the best coffee maker. Now, coffee makers, there could be new ones coming to the market every day, and the knowledge cutoff of the LLM shouldn't prevent it to give you the right answer, right? So it understands that this is knowledge that it needs to acquire from the web and understand based on the responses that are available on the web, come up with something that offers you a realistic idea of what is the latest and best coffee maker out there based on up-to-date reviews from people. And the other idea here is the code execution tool, where the model basically, if you ask the model to, write code to generate, say, financial interest, right? And using the classic interest formula, it basically models that as a code problem, writes code around it, and then uses a code interpreter or the code execution tool to run that particular code and gives you a response back. So these are 2 of the classic examples for tool calling. And touching upon some of what I mentioned earlier about the various different patterns within tool calling that we have. There's the simple, there's multiple, there's parallel and multiple parallel. There's 4 different patterns. And to dig deeper, this is a very good resource about Berkeley Function Calling Leaderboard, BFCL. And what we have here is essentially a leaderboard that gives you the performance of each LLM over all of these 4 patterns. And there's a whole bunch of different LLMs on this particular leaderboard here. Considering it's the most popular function calling leaderboard, there's a lot of new data coming in. Every new LLM typically goes through their evaluation harness, and you'll have data or results on this pretty soon after launch of a new LLM. So what these folks have built together here from Berkeley is essentially 2000 question function answer pairs. So there's the question, which is the input query. There is the function call or multiple function calls that need to be run to serve that input query, and the final answer that needs to be returned back to the user. So that is how the data set is constructed for evaluating and getting results for this particular leaderboard. And like I mentioned earlier, there's a lot of complexity in function calling as well. There's single function calls to parallel function calls, which are multiple sets of function calls to be done to the same function. So say if you have one function available to you, do you want to call that function once or multiple different times with different arguments to get to the answer for the user, right? That just decision also has to be made at runtime by the LLM, right? Because an input query might not require a single function call to be able to serve back the answer. So they have that variation as well, which is parallel. And then there's the multiple variation, which is multiple different API calls. So not necessarily the same API, but a lot of different functions to be called, but multiple of them to be able to serve the answer back to the user. And then there's the parallel multiple variation as well, which is multiple different function calls and many of those, right? So more than one of each call could be needed to put together the final answer. So they have all of these 4 variations that they currently measure, and the columns specifically in blue on the leaderboard actually show some of those individual breakdown results for each LLM. And also there's tests to also make sure that we're not calling functions when it's not necessary, right? You don't want the LLM to be calling functions even for common case queries. So they have specific tests for those as well. And lastly, at this point on this particular leaderboard, we have GPT doing pretty well. It's the top of the charts. So the GPT series have typically dominated these charts, but we're seeing those trends fluctuate as new open source LLMs come in that are pretty good at function calling. I'm going to share the slides later. I've linked the BFCL leaderboard link as well. But your quick Google search will return the leaderboard. Like I said, it's the most popular leaderboard out there for tool calling. But yeah. All right. Now let's cover multi-agent collaboration first. So multi-agent collaboration divides complex tasks into smaller, manageable subtasks, right? And actually software development that we spoke about earlier is a classic use case where you have a grand task at the end of the day that you want to accomplish, and then you have individual agents that carry out specific tasks in a divide and conquer fashion. And then at the end of the day, once all of them have results, they return them back to the LLM. So it synthesizes the final output based on the output that it has received from these individual agents, right? And as part of modeling a particular problem statement to all of these different agents, essentially what we look to do is we role specialize each per agent to a specific area or a role that it needs to play to serve the end task, right? At the end of the day. And like I mentioned, software, it could be a software engineer, it could be a product manager role. It could even be a test engineer, right? So you're writing tests, both unit tests, system tests. It could be an integration engineer to piece all the various components or the various parts of the code that you put together into a much larger infrastructure. So a lot of these roles can be specialized. And in terms of the execution model, what we can have is we can involve either diverse prompts to a single LLM, or we could have separate LLMs as well, tailored for specific tasks. So To give you a concrete example, if we know that a particular LLM is great at writing code, and it's great at coming up with individual functions, for example, that could be an entry-level software engineer, right? So we could utilize that particular specific LLM to carry out that particular role, and you could have different LLMs carrying out these different disparate roles. You could also have a single LLM with different prompts modeling each of these individual components or agents. Depends on the task that we're looking to solve. Both options are available. And then in terms of the idea behind multi-agent collaboration, or the specific motivation here, the AutoGen paper is a very seminal paper in this particular field. It's done by Microsoft. At this point, it's the most popular framework, right there with LangChain and a lot of the other options. And they had a lot of good justification for coming up with this multi-agent structure, which is essentially to make sure that we specialize and focus each of these agents on isolated subtasks. And once they generate their outputs individually, you could make them transfer the output back to the LLM, or even coordinate amongst themselves. So as they generate an output for a particular subtask for the overall task that one particular agent is carrying out, it could send intermediate results back to a different agent, which can then process these results and then carry out some of its own functionality and then send it back to the first agent. And then you could have some of this to and fro pattern going on in between agents themselves before they send their final results over to the LLM to synthesize the final output. So a lot of different patterns within multi-agent as well, in terms of how we structure the particular problem statement, and how the flow of results, both the intermediate results and final results from the LLM, a lot of ways to model that as part of multi-agent collaboration. Now, I mentioned about AutoGen. There's Crew AI as well. LangGraph is another popular one. So these are some of the frameworks that were currently being seen in the field, being used for a lot of these multi-agent use cases. I've linked some of those here. Open source platforms. We actually have ChatDev is also another particular popular paper that came out back in May or so this year. And the idea behind ChatDev was that based on a multi-agent setup, they essentially showed how we could run a virtual software company, right? So all of these different roles that I spoke about, whether it's a program manager, product manager, software engineer, QA tester, all of those coming together via various different LLMs in a multi-agent collaboration setup, and thereby being able to translate business requirements into code that's tested and functional and is able to be integrated in a broader infrastructure setup. So they essentially structured the task of running a software company with all of these different agents. And I've linked the paper here if you want to take a look. But this was one of the seminal papers, one of the initial papers that showed that the possibilities of multi-agent collaboration. Now, the other aspect here to discuss is like human teams, if there's any missteps with AI agents, you can easily rectify them. You can in fact list some of the most common issues that a particular agent might see as it's carrying out its particular specific task, right? And within the prompt, you could list certain common case failures and common case solutions as well. So it could just look that up, and if it hits a problem, it could utilize some of that knowledge and be able to rectify some of the issues that it's seeing in the environment as it's carrying out its task. And multi-agent, I'd say, is probably an area that's receiving a whole lot of traction at this point, advancing pretty rapidly. People are figuring out new areas to model as a multi-agent setup and carry out a lot of these tasks pretty efficiently, going beyond a singular LLM setup that we had earlier in the year. The trend is now shifting to getting all of these agents together for the particular problem statement that you're looking to solve, and then having the LLM interact with these agents via APIs, or calling them through other LLMs, or even a different instance of the same LLM with a different prompt. And then all of that orchestration then feeds back into the main LLM, and there you have your results, getting generated for the particular task that you're looking to solve. So that is a trend that we are currently seeing in the field, going from singular LLMs to a multi-agent setup. All right. Next, I have our benchmarks. I'm going to go back to reflection as well. Let me see if I can. There's some issue with the slides. Let me stop sharing for a bit. All right. Can you guys still see my screen?
Not yet.
How about now?
Yes.
All right. Perfect. All right, so reflection is another agentic design pattern, which is pretty simplistic and still yet very popular. So as part of reflection, what we do here is that the LLM starts with a first attempt or a baseline response for the assigned task, right? So it comes up with an initial response. You could be asking it a particular question. You could be asking it to generate code. It'll come up with an initial response. And then what we do is we have with the same LLM, or you could, like I mentioned earlier, you could actually involve a different LLM as well. What it does is it reviews its initial output, figures out and you could have your own evaluation dimensions, right? You could look at accuracy of the initial response. You could look at the efficiency. Was it terse in its output? Do you want a more verbose output? A lot of these different dimensions could be evaluated. You could look at the style as well. And then it provides self-feedback on some of these areas for improvement. And based on this feedback, it revises its initial response based on the issues that it detected, right? And you could carry out this cycle multiple different times, so this could be a multi-turn cycle. And with each round of feedback, you're refining quality of the initial response. Obviously, at some point, you'll hit a plateau, but you could have a discrete set of iterations here, a static set of iterations with, say, a couple of different iterations, 2 or 3 iterations, 5 iterations, or you could run this iteration loop until you figure out a particular level of quality on, say, some quantitative metrics, accuracy or style, if you're defining some of these metrics, and make sure that you have a response at the end of the day that satisfies some of the initial metrics that you had. So this is the idea behind reflection, which is to make the LLM self-reflect on the output that is generated, refine it, and get you a much better output at the end of the day. Now, this is classic reflection. There's also a reflection with tools where we could incorporate APIs or tools for some of this evaluation that I just spoke about, right? So if you have a mechanism or a particular code base that generates some of these metrics for you, you could actually call that as part of the evaluation phase, and understand what the current set of metrics look like. And based on the values of those metrics, you can carry out another couple of loops if necessary, or if this satisfies the metric thresholds that you set initially, you could send the output back to the user. So you could go beyond reflection, self-reflection, and integrate tools as well. You could also if it's code that's being generated, you can run through tests that you've already set up to ensure that it's correct, right? So for code, we could model this as a test case, problem where it can go through certain tests and ensure that we have functional correctness as part of its evaluation step in the loop. If it's fact checking, we could look at standard databases. You could look at internet sources to verify factual accuracy. And the idea is, at the end of the day, you can carry out iterative correction based on the feedback that you've accumulated, either through the LLM itself, through a different LLM, or through tools, external tools as well, that the LLM has access to. So that is the idea behind reflection. Now, we've got a multi-agent framework here as well. So we looked at multi-agent collaboration earlier, and so this is an idea that combines both of the patterns, right? So multi-agent and reflection, where you could have an actor that focuses on completing the task and producing the initial output. So it's the role here is to just generate the initial output, right? And you could have a critic, which is the evaluation agent that evaluates this particular output and figures out the particular flaws and changes that need to be made. And via some constructive and actionable feedback, it can send some of this back to the actor for it to refine and generate the next set of output. So this collaborative improvement process works pretty well. And it's, it leads to multiple different iterations where the output quality gets higher and higher with every iteration, and obviously until a point where you reach a plateau. And this process allows the LLM to figure out certain nuances, certain specific changes that it needs to make within its output, and works way better than a single agent setup. And I have a quick example for a code use case that we
Aman,
have here. Yes,
Aman?
first. Yeah.
Yeah, if we can probably wrap up in another 5 minutes and keep the 5 minutes for question answering.
Yeah, sounds good. We have time till 12:15 Pacific, right?
3:15. Oh, yeah, so take your time.
Yeah. Yeah, that's fine. I'll wrap up in the next 4 or so minutes by 12:05 Pacific. So as a quick example here, like we discussed earlier, right? The coder agent comes up with a particular task prompt or runs a particular task prompt, generates the first draft of code. And then you have the critic agent, which takes this code and comes up with actionable feedback. And thereby you start your revision cycle to refine that particular code. So that was reflection, and we can go back to particular. I think planning was the other one. I have a couple of slides here, so shouldn't take too long. Should be able to wrap up by 12:05. So planning is another agentic design pattern. And what this enables the model to do is to come up with subtasks that it needs to achieve to carry out a particular end goal. So, for example, if we give the model a problem statement of doing online research, an AI agent can figure out that it first needs to identify certain subtopics, that it needs to look into, figure out sources that are relevant and credible for figuring out information about these subtopics, synthesize all of these findings into one particular area, structure it well with sections, subsections, tables if necessary, or any particular plots that are necessary to show trends, and compile all of this into a report at the end of the day. So the idea is to split the task into various different components. And compared to what we have currently with LLMs, where they essentially, when you give them a task, they try to achieve that particular task in one shot. What planning enables us to do here is to come up with individual substeps and adjust based on feedback at each stage of the process for each particular substep, what it can do differently and how it can achieve, a particular substep better, and course correct its trajectory as it's carrying out all of these different substeps. So at the end of the day, you have an output that is optimal based on the LLM's criteria. And to give you a particular example here, if you look at the figure on the right, the prompt to the LLM is to render a picture of a girl in the same pose as a boy in the initial image. So to carry out this particular task, the model needs to first determine what the pose is within the input image. So it does pose determination, pose detection by running open pose, for example. And then it generates a new image both based on that particular pose as well as the input image to get you a final output, right? So this is the decomposition of that in the original task that happened here to get you a result at the end of the day. And planning versus deterministic approaches. For straightforward tasks, a fixed sequence is actually what you would like because it's much more predictable and much more effective actually. But for complex tasks that involve multiple steps and can be naturally modeled as a multi-step execution pattern, some of those tasks are what planning really benefits. And like I said, it enables course correction and dynamic decision making as well as it's carrying out each particular subtask. And it can select tools at every step of the way. So the design pattern of tool calling is very relevant here as well, where say in the prior example, we had post determination. So it needs to come up with what particular tool or model that it needs to call via an API to carry out post determination, right? So there is tool selection also involved here. All of this is then put together, the outputs of various stages to get you the final output after all of these subtasks are executed one by one. So this is the idea behind using a deterministic approach for some of the more simplistic and straightforward use cases versus using planning for something that can be naturally modeled as a multi-step problem. All right. That brings me to the end of my talk, and we are at 12:05. Happy to take any questions. Let me stop sharing. All right.
So when we talk about the function or a tool calling or API, right? So I believe that it boils down to just an API, because whether you're calling a web search or whether you're calling another LLM or something like that, it's going to be like an API call, even the text to SQL, right? For example, you're calling through an API. Is there any other methods other than APIs we can deploy in terms of tool calling or function calling?
Yeah, that's a good question. The reality is that we can model a whole lot of different processes as APIs, and eventually what we have at the end of the day is API calling when we talk about tool or function calling. But even with, say, the best example of something of this sort would be Anthropic's computer use that they just recently announced a couple of weeks ago, where the model is now able to control your computer, carry out, day-to-day tasks. If you're looking to buy something online from Amazon, or if you're looking to schedule a particular meeting with a colleague of yours, all of this is modeled through API calling, but there's more than API calling that happens, where it's taking screenshots of what's happening on your screen, figuring out if it needs to call an API or if it needs to carry out something visually on the screen by moving the mouse pointer. So there's various different methods to get there, but API calling is definitely the preferred way because it's more deterministic. And we have APIs for a whole lot of software processes that we have, right? Even external tools or software that's available to us, a lot of that is programmable through APIs, right? So we are definitely leveraging the API framework, but we are going a little beyond that now with, computer use, for example, where if you do not have an API available for a particular software, like your calendar, for example, it will visually carry out based on, understanding your screen and taking screenshots of your screen, carry out some of that functionality. So I'd say those are two of the paradigms that come to mind, but API calling is definitely the bigger portion at this point. Does that answer?
Just another.
Yeah, go ahead.
Yeah. Definitely. Just nobody has another question actually, like in terms of like patient, like say OCR kind of activities, right? Where you talked about Anthropic comes up with a recent model. So for example, instead of you're using an OCR skill in the LLM or just an OCR like a document intelligence kind of thing or text track kind of thing, we can use something like this kind of features to just capture the first name, last name, phone number, and then fill out another form in real time, and then you can do the further processing, right? Because you get a filled in form from the patients, and then you have to carry out further processing in the provider's offices and stuff like that, right? I think this is something achievable through this way.
Yes. Yeah. So OCR capability currently exists with off-the-shelf multimodal LLMs. So in fact, if you feed GPT, a form, a handwritten form, even let alone a printed out form, it is able to OCR through your particular fields, return the OCR'd form in, say, a structured format like JSON, YAML, whatever it is that you require, or even just create a bullet list of all of the fields, the key values of all of these fields. And then you could feed that into an LLM that can interact with your screen with, say, computer use from Anthropic. That's a good example here again. And fill in the, the similar fields if it's a different form that you're looking to fill, or carry out some analysis with the fields that you acquired through, running OCR on the initial form. All of that post-processing can definitely be done. So that's a good use case. Document intelligence in general, I think, is going to be pretty transformational as a field with Agentic AI. So I think that's a very good use case.
Thank you.
I have a question. Thanks. This is Meeta here. Thanks for a great presentation. So in your slide where you were talking about the agentic framework, we assumed that the LLM is being used as the core engine or the brain, and it has the capabilities of doing high-level reasoning for carrying out, or at least to call different modules and tools or functions.
Right.
Does this assume that the LLMs that are being used here are capable of doing high-level reasoning? Because I'm asking this question because there is a lot of research that says that LLMs today aren't capable of doing that. So how do we neutralize that aspect of it?
Yeah, so the kind of reasoning that we require here is to map the input query from the user to the corresponding set of function calls that need to be run to serve that particular input query, right? So to make that connection is the kind of reasoning that we need, right? And also to figure out if we need to call a particular function once or multiple times, or if we need to call multiple different functions multiple times. Like I said, there's a lot of different function calling patterns as well, 4 patterns that we currently track. We've seen if once LLMs are pre-trained with some of the data sets that I spoke about earlier, and all of these current leading models are pre-trained on a whole bunch of these data sets and a lot more proprietary data sets as well. But once this pre-training is done, for them to make this connection between the input query and the set of calls, function calls that need to be run to serve that query, with a prompt that's well structured and shows the APIs that are currently available to the model based on your specific environment and what you're looking to do. These connections can be made pretty well, which is how we're seeing, things like computer use, like I said, is a very good example coming up, which is what is driving a whole lot of adoption in the industry as well. Because now you can make a natural query to the LLM and it'll figure out how to get your task done, right? Assuming you have APIs available for what you're looking to do. So that flow that it needs to generate by and connecting all of these dots and coming up with a plan at the end of the day, we're seeing a whole lot of that happening in the field. So there's, obviously gaps. In some cases, the LLM isn't able to figure out what your particular how your particular input query mapped to a certain API because you phrase your query in a certain way or something that it hasn't seen, right? But there's also ways to mitigate that with some more few shot learning within the prompt to make it more robust. So it is a lot of trial and error, a lot of empirical work that is currently happening in the field to figure out that, at least for some of our test cases, we were able to drive this adoption of multi-agent scenarios to carry out functionality. But in terms of reasoning, we don't see a whole lot of trouble, assuming you've pre-trained on enough data and your prompt is structured well with a lot of few short examples. So yeah, that's where we currently stand with agentic adoption, especially in the industry for a lot of real world use cases.
Thanks.
All right, so we've got 1 more minute. Any last minute questions?
I don't think we have any. So thanks, Aman. Nice presentation.
Can we get a link to the presentation?
Yeah, so please share the presentation link. Share it.
Yeah, I'll send it to you, Dr. Das, and you can share it with the broader forum.
Sure.
Perfect. All right.
Thank you very much.
Bye-bye.
Bye.